The interior ceiling of the Pantheon is the largest unreinforced concrete dome in the world. It has survived barbarian invasions, fires, and 2 millennia of earthquakes without a single piece of steel reinforcement. Modern infrastructure tells a different story. We routinely see bridges and highways suffer catastrophic structural failures mere decades after they are built. Even when buildings stay standing, they often exist in a state of constant decay. Many overpasses rely on expensive emergency shoring just to keep from collapsing under their own weight. Despite advanced computer modeling and high-tech manufacturing, we are objectively worse at building long-lasting concrete structures today than Roman engineers were 2,000 years ago. The mechanical flaw lies in our foundational compromise, steel rebar. This dense grid provides incredible immediate tensile strength, but it creates a permanent vulnerability inside the material. Concrete is naturally porous. Over time, seasonal weather changes and ground settling create microscopic cracks, acting as a direct pathway for rainwater to reach the interior steel. Once water hits the metal, the rebar rusts and expands up to 4 times its original volume. This process, known as oxide jacking, forcibly tears the concrete apart from the inside out. Because of this unavoidable internal decay, our cities are built with a planned service life of only 50 to 150 years. By optimizing for extreme strength on day one, modern engineering guarantees its own eventual destruction. For centuries, historians assumed the Romans simply benefited from lucky geography, specifically the highly reactive volcanic ash from the Bay of Naples. But researchers examining ruins like these walls in Pompeii kept finding a strange anomaly: bright white chunks known as limeclasts scattered throughout the concrete. Historians previously dismissed these white chunks as manufacturing errors, attributing them to lazy workers and sloppy mixing practices. That assumption ignores the notorious precision of Roman engineering. These builders followed highly detailed instructions, optimized over centuries. Leaving unmixed clumps in their most important monuments was an intentional choice. Recent analysis revealed the breakthrough, a process called hot mixing. Romans combined dry quicklime directly with volcanic ash and water at extreme, near-boiling temperatures. This intense heat trapped the limeclasts inside the concrete as brittle, highly reactive pockets of potential energy. When a microcrack forms, the fracture travels directly into a brittle limeclast. Water enters and reacts with the quicklime, dissolving it into a calcium-saturated solution that floods the fracture. This solution recrystallizes as calcium carbonate, sealing the crack completely before damage spreads. Roman concrete is a dynamic, actively regenerating system, a material that responds to damage by curing itself. Material scientists have successfully replicated this hot mixing technique in modern labs, watching the concrete heal in real time. Standard Portland cement production is responsible for nearly 8% of all global CO2 emissions. Because our infrastructure crumbles so quickly, we are forced to demolish and rebuild this carbon-heavy concrete every few decades, doubling the environmental toll. The ancient Roman secret has evolved from an archaeological curiosity into a crucial chemical blueprint for solving the modern climate crisis. Integrating these self-healing mechanics into modern construction would drastically extend the lifespan of our cities and reduce our global carbon footprint. The Romans viewed architecture as permanent additions to the landscape, designed to serve for millennia. We currently focus on building fast and cheap, often ignoring the long-term benefits of collaborating with natural chemical processes. Engineering excellence prioritizes resilient systems built for eternity over the short-sighted convenience of obsolescence.